Okay, in this problem we have this rod AB, and at the moment shown, A and B is completely horizontal. So we have A, which is moving down this ramp, which is at a 45-degree incline, and it has a velocity of 2 meters per second and an acceleration of 3 meters per second squared. We're not given anything about this point B, but we can figure some stuff out for it, and we're asked to figure out what this angular acceleration of this rod AB is. So if we look at the relative acceleration equation, we have an acceleration of B is equal to the acceleration of A plus the angular acceleration of AB crossed with the position vector from B to A minus the angular velocity of AB squared times the position vector from B to A. And everything in this is a vector except for this angular velocity. So that becomes important when we're trying to solve the problem. So what I like to do two things. I like to list out all my variables, and I like to draw a kinematic diagram. So if I draw my kinematic diagram, I know this is point B, this is point A, and let's look at this first term, the acceleration of B. We're not given anything about that, so we can assume a positive y direction and a positive x direction. So this is going to be the acceleration of B times the cosine of 45. And we know we can do the cosine of 45 because B is also on a 45-degree incline, and it's going to be AB times the sine of 45J. Now, so this is what AB is. If we look at what the acceleration of A is, we're given that it's 3 meters per second squared in this sort of downward direction. So right here we have our acceleration of A, and it has a magnitude of 3. But we can still divide this up into x and y components. So right here is going to be our x. It's going to be 3 times the cosine of 45i. And right here it's going to be, minus 3 times the sine of 45j. And this is a minus sign because this the vector, when we break it up into components, is pointing in the downward direction, which is against our positive direction of y. Y is positive going up and x is positive to the right. So now let's look at our next term. We don't know what the angular acceleration of AB is, so we're just going to assume it's positive. And we get this is the positive direction because of the right-hand rule. And what is the vector r of B with respect to A? So in order to get this, we start at our A point, we go to B because it's with respect to A, and we have r of B with respect to A, and we said this was completely horizontal, so this is just equal to 10I. And then this angular velocity of AB, and in order to find that, we have to do it one of two ways. We have to find the instantaneous center, or we can use our relative velocity equation. Because I'm working with my relative acceleration equation, ijk components, I think I'm just going to do it with the relative velocity method. So I want to draw another kinematic equation because this one's a little busy already, and I'm going to put down all my information about my velocity. So we know our velocity is 2 meters per second, that's the magnitude. So our I direction is going to be 2 times the cosine of 45i. And coming down is going to be minus 2 times the sine of 45j. Looks a little similar to the acceleration, except just with a different magnitude. Now, we don't know anything about our velocity of B, so let's assume it's positive. So we're going to have the velocity of B is a sine of 45 in the j direction, and the velocity of B has a cosine of 45 in the I direction. Our relative velocity equation is the velocity of B is equal to the velocity of A plus the angular acceleration of AB crossed with the position vector of B with respect to A. So our position vector of B with respect to A is the same as it was with our acceleration, and it's going to be just 10I. And we don't know this angular acceleration, so we're going to assume it's positive. And positive is going to be this counterclockwise direction. So this is going to be our angular velocity. Now if we plug in everything we know to this equation, we have the velocity of B times the cosine of 45I plus the velocity of B times the sine of 45J is equal to 2 times the cosine of 45I minus 2 times the sine of 45J plus this omega AB, our angular velocity, crossed with this 10I. And I forgot my component. This angular velocity has a component of k. Now, this cross product right here evaluates to a k cross an I, and it becomes 10 omega AB times k cross I is a j. So this right here is a j. Now we can do the next step. We can equate our I and j components. So with our I component, we have VB times the cosine of 45 is equal to 2 times the cosine of 45. The cosines of 45 cancel out, so we get the velocity of B is equal to 2. And if we equate our j components, it's equal to VB times the sine of 45 is equal to minus 2 times the sine of 45, which is j, plus 10 times omega AB, which is also a j component. And we can plug in this VB right here, so we get this term turns into 2 times the sine of 45 is equal to minus 2 times the sine of 45 plus 10 omega AB. And we can solve omega AB. Our angular velocity is going to be equal to 0.283 radians per second. And because it's a positive quantity right here, we know it is moving in this direction. Alright, so we found what our angular velocity is. We're right here, and we already said that we knew our position vector. It's 10I. So we have all the information we need for this equation. So let's plug everything into this equation. We have AB times the cosine of 45I plus AB times the sine of 45J, which is equal to this acceleration of A, so 3 times the cosine of 45I minus 3 times the cosine of 45J plus this angular acceleration of AB, which is crossed with this position vector 10I. And again, I forgot this k component. This has a k component, which is crossed with this 10I. And we subtract this scalar quantity of our angular velocity, and this is 0.283 squared times this 10I. So this term right here ends up with a I component in this problem. Okay, so if we do this cross product out right here, this turns into 10 alpha AB. K cross an I is a J, so this is a J component. And this is going to be, we can just leave it 0.283 squared times 10 I. So we have this equation in terms of I and J components, so we can equate our I component. And when we do that, we get AB times the cosine of 45 is equal to 3 times the cosine of 45. And this is a minus, so minus 0.283 squared times 10. And we can solve this equation out for the acceleration of B. And when we do that, we get the acceleration of B is equal to 1.87 meters per second squared. Now, our next step is to take our J components, and with our J components, we can combine all those terms too. So we get AB times the sine of 45 is equal to minus 3 times the sine of 45 plus 10 omega AB. We know what this acceleration of B is right here, so we're going to plug 1.87 in for AB right there. And the only unknown we're going to have is this alpha, this angular acceleration of this rod AB, which is what we're looking for. Now, when we solve for this angular acceleration, we're going to get this angular acceleration of rod AB is equal to 0.344 radians per second squared. And because this is a positive, we know that our assumption was correct, and the acceleration is in this clockwise direction.